So let us recall the separation lemma for metric spaces. Here we don't even need completeness, and just a metric space property is sufficient for the separation lemma. And so it says that if you have a metric space, this is the same statement that we gave for compact Hausdorff spaces, but now we have a metric space. So it satisfies the following property. It says that if you have a closed subset A and X belongs to the complement of A, then there are open sets U containing X and V containing A which are disjoint. And this is the separation property picture that we saw before. You have a closed set A. This is the closed set A, and you have a point X, and you have disjoint open sets that contain these two things. Okay, so let us look at the proof of this result. Proof. So here we will use the metric property, and so for any A belonging to the closed set, there exists numbers which I call epsilon A greater than 0 and epsilon X greater than 0, such that the metric ball of radius epsilon A with center X, this does not intersect A, and X is not contained in the metric ball with center A and radius epsilon X. So what we are doing here, we are taking small enough, so we have this closed set A and you have some point A here. So first of all we are choosing epsilon A so that this radius is epsilon A, which does not intersect A, and this is possible. Since A is closed, which means that A complement is open and X belongs to A complement, so there will be a metric ball with some radius which does not intersect A. On the other hand, there will be another radius epsilon X here. This radius is epsilon X, and it does not contain X. This is simply from the Hausdorff property if you want. So now what we have is the collection of sets U. So take the union of the collection of these metric balls with radius not A but epsilon A by 2, and this is over all the points A in the closed set A, and we have another open set which is the union of the metric balls with center A and radius epsilon X by 2. This is again for all A in A. So now what we have is I claim that first of all X is in U. Secondly, V contains A. Of course, both are open. Both U and V are open. And thirdly, you have U intersection V is empty. So 1 and 2 are quite trivial. 1 and 2 are trivial by the construction of our sets U and V. However, to show that so now to show 3, we suppose that we have a point in the intersection. This implies that there exists an A in A such that Y belongs to the metric ball. Well, let's take A1 and A2. So 2 points A1 and A2 in A says that first of all that Y belongs to the metric ball with center X and radius epsilon A1 by 2, because if you remember that U is the union of all these metric balls here, and similarly you can find a metric ball here, and Y also belongs to the metric ball with center A2 and radius epsilon x by 2. So here actually the notation might be a bit confusing. So this radius epsilon x also depends on the point A. So let me write epsilon ax over 2, and so this is a epsilon a2x over 2. And now since this implies that the distance of x and y is less than epsilon a1 by 2, and the distance of y and a2 is less than epsilon x a2 by 2, and this means that the distance of x and a2, this is less than or equal to, by the triangle inequality, epsilon a1 plus epsilon x a2 over 2 by the triangle inequality. And this is less than or equal to, well, this is actually strictly less than. Now this is less than or equal to the maximum of these two numbers, epsilon a1 and epsilon x a2. So let us call this some eta greater than 0. However, this leads to a contradiction. So if eta is equal to epsilon a1, for example, this implies that a2 belongs to the metric ball with center x and radius eta, but we have chosen for each a we have chosen these metric balls such that it does not intersect a. So this is a contradiction. And similarly, if eta is equal to epsilon x a2, then this means that x now belongs to the metric ball with center a2 and radius epsilon x a2, and this is again a contradiction because we have chosen these open balls such that it does not contain x, and therefore we have that these two open sets u and v are disjoint. So this means that u intersection v is empty. So this proves the separation lemma, and now we have the corollary of the separation lemma that we proved for the compact Hausdorff space case. But if you go back to the proof, you will see that we never use the fact that it is compact Hausdorff. So the same proof actually works for this case when X is a metric space. So I'll just state it, and I will use that lemma in the proof of the Baire category theorem. So this corollary, I'm just repeating the statement. This is for metric spaces rather than compact Hausdorff spaces, but it's the same statement. So here X is a metric space and A is a closed set in X. You have a point X in an open set U, and X does not belong to the closed set A. Then there exists a neighborhood U1 of X such that X belongs to the closure of U1, which is a subset of U, and the intersection of U1 closure and A is empty. And this is the picture showing, this is basically the same picture that we drew before, and the proof is exactly the same as before, since it did not use the compact Hausdorff property. So you can repeat the proof and you will have the proof of this corollary. And now we will use this to repeat the steps that we did for Baire category theorem for compact Hausdorff spaces, and now we will use it for metric spaces. But at one of the last points, we used the finite intersection property of compact Hausdorff spaces to conclude the Baire category theorem, which we cannot use anymore, but for that we have a separate lemma. But let us now begin the proof of the Baire category theorem for complete metric spaces. So to start with, the first step is exactly the same as the proof given for the compact Hausdorff space. So given any non-empty set U0, there exists a point y such that U0 belongs to the point y belongs to U0 and y does not belong to A1. So because interior of A1 is empty, and using the corollary above, we have a neighborhood U1 of y such that the closure of U1 does not intersect A1, and U1 closure is a subset of the open set U0 that we chose. And this is the same step. Now, second one is also almost the same. This is the recursion step, and we recursively defined our open sets UN. So if U1, U2 up to UN minus 1 have been defined, we define UN, and this is also the same as before, but here we make a slight modification. So since XB is a metric space, we choose UN to have diameter less than 1 over n, and we will see what this entails. So because because we have the metric space situation, we can restrict our diameter to as small as possible, and therefore we can choose UN to have diameter less than 1 over n. And now in the third step, step 3, is to show that it suffices to complete the proof. It suffices to show that the intersection of all these UN closures is non-empty. And once we show this, the argument is the same as for the compact Hausdorff space case. And so we just have to show that the intersection of all these closures of UN is non-empty. And for this, we require a short lemma, which we shall show in the case of complete metric spaces. So this lemma states that if you have a nested sequence of closed sets, so nested sequence means C1 is the largest, C2 is a subset of C1, C3 is a subset of C2, and so on. So this is a nested sequence of closed sets. And for example, here we have the same situation where you had U1 closure, this was the largest, then you had U2 closure, and so on. So this was the nested sequences that we defined in step 2 in the recursion step. And so these are in a complete metric space X. Then the condition says that if the diameter of these closed sets Cn converges to 0, so this is now a sequence of real numbers, positive real numbers, and we want that the diameter these numbers converge to 0, then the intersection of all these Cn's is non-empty. And we have immediately from this lemma that this intersection is non-empty, since the diameter of UN closure is equal to the diameter of UN, and this is less than 1 by n. So the diameters, the sequence of diameters converges to 0. So here I am using the fact that the diameter of the closure is the same as the diameter of the open set. And this is not very difficult to show, and I leave this to you as an exercise. And we will use this property to conclude that our intersection of all these U enclosures is non-empty. So let us prove this lemma. But before we go to the proof, I should mention that this nested sequence are all a sequence of non-empty closed sets. Because otherwise, if you just have empty sets, then of course the intersection will also be empty. So it's just to be careful, we always assume non-empty sets. Okay, so let's look at the proof. So we choose for each n, we choose a point xn belonging to Cn. Now we use the fact that the diameters of this Cn converges to 0. So this means that given any epsilon greater than 0, there exists a number capital N such that the diameter d of Cn is less than epsilon for all n greater than or equal to this capital N. And this means that for all n and m greater than this number capital N, greater than or equal to n, first of all, that both xn and xm belong to Cn. This is because Cn and Cm both are subsets of Cn. And secondly, that the distance between dxn dxm is therefore less than or equal to the diameter of Cn, and this is less than epsilon. So therefore we have a Cauchy sequence. This means that xn is a Cauchy sequence, and this means by the completeness that since x is complete, xn converges to some point x for some x. However, note that we have the nested sequence. This means that the sequence for each k in the natural numbers, we have that the sequence, the subsequence of this sequence xn starting at k. So we have xk, xk plus 1, xk plus 2, and so on. This also converges to x, because we are taking a subsequence of the convergent sequence, so it also must converge to x. And note that this implies that x belongs to the closure of ck, but since ck is closed, this is just ck. And this is because all the cl is a subset of ck for all k, for all l greater than k, for all l greater than or equal to k. And so all these points xk plus 1, xk plus 2, etc., they all belong to ck. And because it converges to x, x belongs to the closure, because we are in metric space, so it belongs to the closure of ck. And ck is closed, so the closure is just ck. So this means that x belongs to each ck, which just means that x belongs to the intersection of all these ck's. So this means that this intersection is non-empty. And this completes the proof. This completes the proof both for the lemma, proof of the lemma, as well as the Baire category theorem for complete metric spaces. And so this completes the proof of the Baire category theorem, which stated that both compact Hausdorff spaces and complete metric spaces are Baire spaces. And now we will, in the next lecture, take a look at an application of the Baire category theorem.